Hello physics nerds, we're going to review momentum with this video. I might have done a momentum video beforehand, but I'm going to redo this just to clarify some things and add a little bit more here and there. Alright, so let's start. These are the following topics I'm going to cover: still momentum, still impulse, conservation of momentum, and a few collision and explosion problems. So let's start with our definition of momentum. It describes how much motion an object has, and this is the product of mass and velocity. This is what it looks like, where P is equal to m times v. P stands for momentum, m is mass, and v is velocity. You multiply those two together and you get momentum. And I also forgot to add this right here, where the unit for momentum is kilograms dot m/s, kilogram meter per second. That's our unit for momentum. Here's some other important notes. Objects at rest have no momentum. If they're at rest, that means velocity is 0, and when you multiply by 0, you get 0 momentum. And momentum is a vector. So let's add that little arrow right there at the top. That indicates it's a vector. And this follows the direction of the velocity. So wherever the object moves, the direction of velocity, that is where the momentum is going as well. Alright, now in order to change an object's momentum, you have to apply a force. And when you multiply this force with its time duration, this is what we call the impulse. So let's start with objects' change in momentum. So delta P, delta meaning change. When you change an object's momentum, you could either change its mass or its velocity, but realistically, you're most likely going to change its velocity. So m/delta v. And when you apply that force over the times its time duration, you get F times t. That is what we call impulse, J. So we have here this four-way relation in which these two are essentially starts with these two equaling each other, where the change in momentum is equal to impulse. But you could set it up in this four-way relation, pluck out two of these to solve problems. They're all equal to each other. Now the unit for impulse is Newton seconds, Newton dot seconds. Alright, now when you change an object's momentum, it's likely because of a force, and where do you encounter forces like this? Collisions, car accidents, or explosions. So in these type of problems, you're going to see this idea of conservation momentum, where the total momentum of a system remains constant, never changes. So here's how we represent an equation. The momentum before the incident is equal to the momentum after. But I must indicate here, this is total. So each object in the system may have different momentum values before and after the event. So let's say we have two objects, for example. P1 initial plus P2 initial equals P1 final plus P2 final. So object 1, P, could start out with a momentum of e. But it went down to 2 after the collision. What's important to note here is that the total momentum has to stay the same. So in order to balance this out and keep the conservation momentum happening, let's say object 2 could have a momentum of 3. In order to make sure that total momentum is conserved, it could go up all the way to 9 after the incident. That's an example of how they can have different momentum values before and after. So each individual object could change its momentum in different rates as long as the total momentum stays the same right here. Look, momentum is transferred from one object to another. Alright, So there are two types of conservation momentum problems, and they could be either collisions or explosions. Here we're going to start with collision. That means you have two objects that are moving and they hit each other and kaboom. So let's start here. Ew, I don't like this highlighter. Okay. So here, let's start with mass 1 as 2,000 kilograms. And it initially travels with this speed. So object 1 with its initial velocity is equal to 20 meters per second. Collides with a 1,000 kilogram car. So that's our second object here. 1,000 kilograms. At rest at a stop sign. So initially the other object was at rest. Now we've hit the collision. Now we're looking at afterwards. If the 2,000 kilogram car has a velocity of this, so object 1 after the collision is going to go this way. 6.67 meters per second after the collision. We got to figure out the velocity of this one after the collision. So we're looking for v2f. So let's start out with our p before equals p after. And since we have two objects, p1i plus p2i equals p1f plus p2f. Alright, now we substitute these values in p1, so it's m1 v1i plus m2 v2i equals m1 v1f plus m2 v2f. You kind of have to memorize this a little bit or start out with this one. You'll only be given this in the reference table. Then it's up to you to sort of expand it into these following forms based on the scenario. So you kind of have to sort of understand what's going on in the problem and then expand it accordingly. So let's plug in our values. Plug in chug. So notice how I'm not writing units. You could kind of get away with this on the regions if you just put everything else on the side like this over here. If you write that off to the side, then you can get away with not putting in units. That's a secret trick I learned. Plus, I don't feel like writing all this work just to save space. So notice here, v2i is 0, so we could just put 0 right there, because anything times 0 is 0. m1, alright, we're getting into this part. 6.67 plus 1,000 v2f, that's what we're solving for. Alright, this one value is 2,000 times 6.67 is 13,340 plus 1,000 v2f. Then you get this. Divide 1,000 on both sides and you get v2f is equal to 26.66 meters per second. Alright, there we go. That's how fast the second car is moving. If you notice right here, the bigger car was traveling 20 meters per second, and then it ended up with a slower speed than what the smaller car has. So because of Newton's third law, they collide together, they experience the same force, equal but opposite reaction. Same force because of Newton's third law. Despite experiencing the same force, their speeds are going to be different based on their masses. So if you notice, the smaller car is going to end up with a higher speed, whereas the bigger car ends up with a smaller speed. That's a way to check for yourself if the numbers you got actually make sense. Alright, explosion example. So what characterizes an explosion scenario? So that means you have like an explosion event like a bomb, guns, or two objects initially at rest together, and then something happens and they start flying out. It could even be an example of two cards attached by a spring. That's an example of an explosion. But here in this example, we have a rifle firing a bullet. That's an explosion collision example. All right, so here, let's start with this. M1 is 4 kilograms. M2 is our 20-gram bullet. Keep a note, we had to put it in kilograms. So this is what it is. You move the decimal place 3 times to the left to get kilograms. So rifle and bullet, they're at rest together. After the gun is fired, that's where the speeds happen. So initially they're at rest before the gun is fired. So both of them, V1I equals V2I, they're both at rest. Now we're going to look at what happens after. The bullet has a velocity of 300 meters per second. We're looking for the recoil velocity of the rifle, so that's V1F. Okay. Let's start out with P before equals P after. They're both at rest. So P1 plus P2 equals P1F plus P2F. They're both at rest, so it's 0 on this left side, so we get this. Notice right here, this is characteristic of explosion examples. Any explosion collision problem has this sort of thing. So they're likely going to go off in opposite directions. That's why the negative sign is there. But they're going to have equal magnitudes. This is only for explosion examples. Both objects have equal momentum after explosion. But because of their different masses, they're going to have different velocity values. So you're going to definitely see the rifle have a smaller velocity than the bullet. So if the bullet goes out 300 meters per second, you should really expect the rifle to have a recoil velocity of a much smaller value. All right, so let's actually solve this. So M1 is 4 kilograms times V1F equals a negative 0.02 times 300 meters per second. So 4 V1F is equal to negative 6 V1F is equal to negative 6 divided by 4, that's negative 1.5 meters per second. That's still kind of fast. Anyway, the negative sign meaning it's going in the opposite direction. So it's easy to imagine when you fire a gun, the rifle pushes back on you, whereas the bullet goes forward. So one goes forward, the other one goes backwards. That's what we mean by this answer. But anyway, that's pretty much the gist of what you need to know from this unit.